And that's why I start with compactness. So every time there's an astronomical object discovered, that most one of the questions connected to the discovery is about compactness, to classify the object. And then if the compactness is reasonably small, it becomes of us of interest of a relativistic astrophysicist. So we all know that there is this natural scale for length and for time, which is given by the mass and then just the constants of nature, and the numbers are like this. So for instance, there is a class of supermassive black holes, and an example of our nearest supermassive black hole, such as Arius A, then the time scale is about 17 seconds. And for a microquasar, this time scale is to the order of 10 to the minus 5 seconds. And then if we want to measure the compactness, then we must know the mass, and knowing mass is an easy task. We know pretty well how to do it. We measure this shift of spectral lines, radial velocities, and then we deduce the mass. But we also need to measure the size of the system, and that's more tricky task. There's no direct way how to measure it, and we usually infer the size from something else, and this something else is most often light curve, and the variability which we see in the light curve. And we are looking for the shortest variability possible, and then from this we deduce the size of the object, and we have the compactness. So let me briefly remind the basic characteristic timescales of black hole accretion, which is at the first place the timescale connected to the inward circular orbit, when the flow changes from the almost circular to almost free fall, and loses rotational support at the marginally stable orbit. And then I will be using these units, mainly this one, for expressing the numbers. So in these units, the time scale connected to the marginal orbit is something like 90. Then there is another time scale shorter than this one, connected to the marginally bound Keplerian orbit. And so you see this 15 to 90 is shorter. But then if you have stresses in flow, and in particular those of non-hydro origin, magnetic stresses and so on, then this perhaps is not a time scale which could be observed from a system. And then that's why most people believe that if you possibly observed anything that would be most probably connected to the ISCO, or the sonic point close to this place, while this is not practically observable. And in fact, those QPOs we believe that come close to this region, these high frequency QPOs. But then still there is another time scale, even much shorter than these two. And it's the photon orbit time scale. And the advantage of this is it's not connected to a flow. It's connected simply to the basic properties of the black hole, of the system, and its mass and spin. So for a non-spinning black hole, the time scale is about 20, even much more shorter than the time scale of marginally bound orbit. So this would be the real proper shortest time scale which could be observed in light curve. And the talk is about if this is possible to find in the present instrumentation in data which we can get from sources of various types. So we consider that there is an accretion disk, and on its surface there might happen some events connected to to magnetic field flares similar to solar flares, which live for a certain amount of time and produces enhancement of radiation. And then the signal from these flares can reach the observer by various ways. It's a direct way. And then we also have these looped photon trajectories which will around the central object, central black hole. And then there will be a different time delay between the direct image and this looped image. And this could be searched in light curves. And we consider here two scenarios. It's a disk flare, if there is an accretion disk. And corona flares, if there is no accretion flakes, so the flow is just hot and optically thin that surrounds black hole, and then there might be these flares. So we investigate if the signal which we get from the looped image would be still strong enough so that we'll be able to at least marginally dig out from data. So let us first concentrate to the scenario where there is a disk. The disk is optically thick, so we only consider the flares which happen on one side of the disk. And this then is the direct image, and this is the looped image. If the event is on the other side of the disk, it's basically the same, but then the ratio would be of these fluxes of these two would be much lower, because you wind not only the second one, but even the first one. So let's take it like this. And then what we calculate is the time delay here and the ratio of fluxes between these two. So we have this thin disk. We assume something about the distribution of these flares. So the random distribution in radius in the azimuth direction. The flares have some distribution in lifetime, and we consider basically this as a hotspot with a definite size. And the light time is kind of partially random and partially proportional to the size of the spot. Then we have these two images, and if we calculate the differential cross-section, we calculate the impact parameter and the value dB over B, then close to the black hole, this is proportional to V2 minus 2 pi, which then gives the ratios like 1 to 50 in flux. But then there are various geometric effects which may improve the ratio to be approximately in this range. The good news here is that the time delays we get will be quite coherent, so that will help us a little bit when analyzing the data to see the effect. So here I make a plot of the time difference between the direct and looped image, and you see here the plane of the accretion disk, and then generally the observer is to the right, but here we are looking along the symmetry axis from top. And colors here code the value of the delay, which is expressed then in these natural scale units. So here the blue region corresponds to the time delay, which is between 35 and 40 approximately, and the size of this region you see is a few gravitational radii, or it's in units of m. So then if you are a little bit inclined, then the shape changes, and generally this area where from which we have coherent time delays in this range is larger. And if you incline even more, then it covers the almost all vicinity of the black hole. Then this region here, the shaded part is the part where the looped photon is obscured by the inner edge of the disk, which is at ISCO. So you can't quite see any events going from that region which are looped. So that's for the time delay. And we also calculate the flux ratio, which is the most crucial thing here. And as I showed the number, that it's an logarithmic scale, so you see that this green one is somewhere here. That's this 500, 1 to 500 ratio. If you incline this, that you are becoming to have more yellow color, so they improve the ratio, but only in a very narrow range. And then unfortunately, if there was not this obscuration, then you would have a ratio here which would be almost 1. But obscuration is there, so we can't quite account for that.
What's causing the vertical asymmetry?
Why it's not vertically
Symmetric.
yeah. Because the observer looks from this side, and I only plot photons which go on this part, of this top part of the plot. So if the place is here, so you have one trajectory going this way, and the other going that now it's difficult to go kind of this way. And then if the place is here, then one goes like this, and the other goes like this.
I see, but you're always up on
Yeah.
that side. I see. Okay.
That's why it's not symmetric. Okay. Fine. This is the case with corona. So this is moved further out, and you are left with a hot optical thin flow. And then essentially the event can be anywhere. And now it's there's spherical symmetry, so also the plots will be symmetric. And we assume basically the same, that now the distribution is 3D, and the difference here is that we see not the looped image, but we see the direct one and the so-called first indirect one, and that improves the ratio quite. So then the ratio is like this, but then the coherence of time delay is not as good as it was before, and we have some larger spread. And it kind of compensate between these two. So this is the time delay, and that now it's obvious that it's symmetric. So if the observer is here, then if the event is just behind the black hole, then this time and this time is the same. So there is 0 time delay here, and you have some increasing time delay in both directions. So again, then the interesting region would be somewhere here, which means that we are interested in this and this part of the space. And if you look on flux, the flux ratio, then it's also obvious that if you are behind the black hole, then it will have 1 because of the symmetry, and then the flux ratio decreases. And in fact, this range also corresponds to this and this part, and it plays against. So while we have greater time delay going this direction, we have also decreasing flux ratio going this direction. So there will be this region, which in effect is interesting from the observational point of view, because here the flux ratio is too small, and here the time delay is 0, so we can't quite get anything from there. And now how this is possible to detect. Because of the flux ratio is so small that we have only a chance to see the direct image and then the first looped image, and there is no hope that we could detect anything from the photons which more wind than 1 times around. So the light curve of the signal then is not periodic in the sense that if you analyzed this in the standard way using Fourier transformation, you would get any peak. And so what we propose is much better here to use is the autocorrelation function, which basically gives you the sense of how signal at one time is related to the signal at time which is delayed by some interval. And then we expect in the autocorrelation that we will see an excess and a time scale which corresponds to the photon orbit. And that might be a direct signature or the direct way how to measure the mass of the black hole. There's also possible to test some theory of gravity by this, of course, but that's the future stage. Here in this table I summarize various sources that we may apply this to, and you see here the distance, country, time scale, and the most important here is this last column, which combines the typical count rate that we get from the source and the time scale of this photon orbit in the source based on its mass. So if you multiply these two, you basically get number of counts per this time scale. And then you see that if we start, for instance, with galactic black holes, with microquasars, then the number is in best cases 1. But it's more often less than this, so the range is like this. Then we have visual axes of various types. That does not matter, because then here the ratio is quite hopeless. We have too little, especially in case that the visual axis of the stellar mass origin, then we have too low photons to see this. But if it is an AGN, that they have, first of all, quite, on average, quite high count rates, and the time scale, because of the mass is so large, is quite long, and then the number of photons we may detect per this time scale is reasonable. So digging in light curves for sufficient amount of time, it could be possible to recover such an effect. And here we do some estimate, so zero level assumption. If we assume a light curve which consists of a peak and then just a noise, this peak is a signal because of an event, and then we have noise. So this is the amplitude of the peak, this is the noise, and then it's periodic by n time units. And then we can define the autocorrelation function, which is also periodic in this, and define criterion under which we recover in the autocorrelation function the signal against the noise. So we get this ratio, which basically gives us the condition, and then you see it depends on both things. Of course, the less noise we have, the better. And to really see how it looks like, we did a simulation based on the calculation of time delays and fluxes I showed before. And we assumed some distribution of flares in the disk, so that's the disk case, and did the light curve and the autocorrelation function. So here you just concentrate on this black line, which is how the situation was like if we would not include the effect of the looped photons. That's just the autocorrelation function, which goes down to 0. Then this basically here you erase the noise, and then what happens here is not quite important. It's much larger time scales. But then the red one here in this region is there is this bump which exactly corresponds to the effect of loop photons. So that's kind of a little bit idealistic case, and we did more of these simulations. This one came out as the best one, so as I'm showing this, but also in the others, there is clear indication that there is a kind of break against the profile of the autocorrelation function where no multiple edges are taken into account. So with a little bit of luck, and if the light curve to analyze would be sufficiently long, I think there is a possibility to detect this effect and infer the mass of the black hole just from basic principles. That's it.
Some time for questions, discussion.
Let's assume that you are able to get such autocorrelation function from observation, and how are you able to precisely determine that the shortest time scale is basically on that hub, which is quite diluted?
Well, this is not the only thing you do. First of all, you do normal Fourier transform, and then you will see how the power spectrum looks like, and there will break at high frequencies that you count. And if this, and it should also appear here that if there is a particular frequency connected, for instance, to marginally stable orbit, that there will be a peak here. That's obvious. And if you have still, which is on a lower time scale than this, then you may expect it's connected to this effect, because there indeed is not any shorter time scale which could produce something. So if this is the shortest one, then it's because of this effect.
In the
Go ahead. Yeah.
in the power spectrum, what do you expect to be occurring at the shortest time scale? Nothing. So
no, nothing. This will not show up in the power spectrum.
No. I understand that because it's a very weak feature, but you don't expect the power spectrum to extend beyond the frequency corresponding to the photon orbit, right? So it must.
Well, then I expect it's the the end of the flow, perhaps, because if this all assumes that the flow really ends at the ISCO, and then the photon can go through, so it's optically thin, and there is not much happening in the Planck region. So then the time scale would be the one connected to the ISCO, which you will see in power spectrum.
Is this detectable for Sagittarius star?
No, there's not a disk there, so.
Well, there are flares occurring.
I don't know really. I've spoken to people who do analysis of Sagittarius A star flare, not only in X-rays but in near infrared, and they were quite excited, interested. They told me that nobody so far considered this, and in fact they are now only taking all the data they have, and they are trying to find some patterns, global ones. So far they were only interested on this interesting part of the Lyca where there is an outburst of flare coming from Sagittarius A star. So let's see.
Yeah, if you have really a sea of flares, let's say on top of the corona of the disk, is there a point at which, when you have too many, you cannot use?
Yes, there is. That first of all, it depends quite a lot on the time of life of the flare. If this is too long and it spends almost all the orbit, then it makes things worse, and you lose the advantage. But in these AGNs, that's good news that the flares are not connected to the mass. They are just magnetic effect, so there is a fixed time scale for them, and the orbital time scale in AGN is so large that they will only last a small portion of the orbit. But if a flare which stays and orbits there, so you may forget about it.
I mean, I guess it's related, but let's say even if you have short flares, but you have many of them at given radius and many of them at other radii. So at which point there might be a point where if you have too many, you must use the information in the autocorrelation function.
Yeah. Then it smears this out if you have too many, but you have to have really too many.
So it might not be a problem. I guess yeah. Clearly, if you have several like this, you can take the autocorrelation function, you're fine. But if you put too many, then it becomes a problem, and it's an issue of the repeat cancel or something.
Yeah. If it is like that at a given rate or a narrow range of radii, they overlap in time, then you are going into problems. If they are separate, it's perfectly fine. It works beautifully.
No further questions. Let's thank the speaker once again.